Network scanners and vulnerability analysis tools are invaluable in discovering fingerprinting data about network hosts. These fingerprints consist of a diverse and large variety of attributes. Fingerprint similarity can provide very important insights for network security administrators when tackling threat propagation or conducting forensic analysis. We developed ScanSphere, a network mapper tool that uses off-the-shelf scanning tools to fingerprint hosts in a network or across various networks, and then cluster these hosts based on the similarity of their whole or partial fingerprints. Our tool generates a high-level map of the network, where hosts are clustered according to their fingerprint similarity. In order to tackle the curse of dimensionality, our approach uses network embedding techniques. This tool provides network administrators with a holistic view of the network and assists them in real-time security decisions regarding threat management and analytics.
ScanSphere's design process and development was executed in 5 stages. We begin by scanning the client's network and retrieving data on every host scanned, before preparing this raw data for database transfer to a secure MongoDB server. From there, the program uses an intricate sorting method to sort this raw data into nodes and edges in the server and construct a directed, weighted graph. This newly embedded graph is then clustered using k-means clustering and visually plotted. We use the elbow method to determine the optimal number of clusters. Finally, the GUI for this tool is built using Python's Katinker library for a user-friendly experience.
For data collection, we are using Python Nmap library to scan the host and the information contained within each host. Currently, ScanSphere offered 3 scanning options: single IP, IP range, and specific IP addresses. After the scan, the raw Nmap data will be directly transferred to our MongoDB server. Here we see a snippet of our data collected in the MongoDB servers.
At this point, the database is holding raw Nmap data to be converted into nodes and edges. This implementation required a very extensive process in order to properly reference MongoDB documents to create separate host and attribute nodes and to account for every attribute key value pair saved. You can see one example document from each collection here. Additionally, the database contains a 5th collection called Counter, which assigns each node a numerical ID suitable for graph construction and graph embedding.
Graph embedding is the process of mapping complex networks to vector spaces while preserving the properties of the network itself. Vector spaces can be more useful to data scientists than raw graphs alone and are often simpler and faster than their graphic counterparts. Our tool uses 2 such techniques: structural deep network embedding, also known as SDNE, and node-to-vec, provide a more comprehensive analysis. SDNE joins first-order and second-order proximity to optimize a semi-supervised model that is able to capture nonlinear network structures. This is unique when compared to other embedding methods. Meanwhile, node-to-vec uses random walk to optimize a flexible approach by sampling network neighbors of nodes, which provides a variety of differing neighborhoods.
Here we see our network dataset as an embedded graph using SDNE. This graph contains 68 nodes, 129 edges, and 30 attributes over 3 networks. For node-to-vec, this graph contains 76 nodes, 142 edges, and 31 attributes over 4 networks.
After we embedded our graphs, we're left with a large amount of network data that we want to group based on similarity so we can actually interpret this data. K-means clustering yields several advantages. It's relatively easy to implement, especially with the sklearn library. It can scale to large datasets, and this method easily adapts to new examples. In other words, with each scan yielding different network structures, this tool can adapt its clusterings to accurately represent new similarities found within the network. Having to manually choose the number of clusters can be a pain. Luckily, we have this nifty technique called the elbow method, which helps us to determine the number of clusters. Let's look at one clustering example from each of the gem methods we used. Here is a plotting of the elbow method. We can observe the elbow, the point at which the slope changes drastically, to be at k equals 4. In other words, this method implied that 4 clusters was best for our SDNE dataset. Using similar logic, we reasonably interpreted the elbow to occur at k equals 5 for node-to-vec. Our program tells the user how to interpret the elbow method and then enter the value of k they interpret to be optimal. For SDNE, we entered 4, and after that, sklearn's k-means library clustered our SDNE data into 5 such clusters, which we can now more definitively interpret. Again, the same was done for our node-to-vec data. Based on the elbow graph, we entered 5 as the optimal k value, and so we received a plot with 5 clean and compact clusters based on data similarity. Now that we have our clusters, how do we make this data useful? In this clustered graph, each node shares a 1-to-1 correspondence to a scanned host. This means we can access the raw data and connect these data points to actual host devices scanned. Depending on particular graph results, the user can then predict any trends within their network. For example, if one such cluster, which we can call cluster A, comprised a certain part of the network, these devices must be closely related. For network security purposes, this could imply shared vulnerabilities. If a device in cluster A was compromised, the client might be encouraged to look at other devices in cluster A for similar vulnerabilities.
To see this tool in action, please view the included demo video.